in Baltimore, Maryland. This is live coverage of a real-time spaceflight operation as controllers prepare the James Webb Space Telescope for work. On the morning of December 25th, a massive rocket called an Ariane 5 lifted off from a state-of-the-art facility located in French Guiana. On board, the James Webb Space Telescope, bound for a point in space 1 million miles away. The process of preparing Webb for actual operations is called commissioning, and the majority of that work is taking place here at the Space Telescope Science Institute in Baltimore. What you're looking at now is some incredible footage, actually taken live from the James Webb Space Telescope during launch. And here we now see the Mission Operations Center in Baltimore. No worries.
And the emitter status is changing.
So I'm your host, Michelle Thaler, today, and this is really a momentous and historic event that you're looking at. We are actually going to be with you live as we finish the major unfolding of the James Webb Space Telescope SUNSHIELD. This is something that has never been done in space before. This is a technology that's never been used in space before. I am really, really excited to be here. And I want to give you a little bit of a sense of what's going on here. A lot of things have been changing very rapidly. We have a beautiful set at Goddard Space Flight Center where we were going to give you a very well-rehearsed live broadcast. Because of the resurgence of COVID, we are no longer operating on that set. And so those of us who can be at home are at home for the protection and the health of our colleagues, and the people that absolutely need to be at the Mission Operations Center in Baltimore are there. That means that I'm doing this from my home and that you're looking at something that is also unrehearsed. This is a live event that we haven't really had a chance to put together in a very polished way. So as we do this, we're all in this together. I ask for your patience. If things are a little rough around the edges of this broadcast, that's the reason why. We also received a foot of snow yesterday here in Maryland where I live, so I'm having sporadic power outages. Hopefully we won't be worrying about that. But the reason we've decided to do this live is that this is something that everybody around the world is with us on. The James Webb Space Telescope is a true milestone for humanity. And it is a really historic, momentous day, and we want you with us on this day. So later in the broadcast, we'll be taking questions from social media. But to begin with, I want to begin discussions with somebody that's been with the Webb mission for quite a long time. And this is Keith Parrish. Keith Parrish, let's see, your title now is the spacecraft deployment engineer. Is that correct?
No. I'm the commissioning manager for Webb.
Commissioning manager. Thank you very much. The commissioning manager. Yeah, that's right.
Yeah.
So
good morning, Michelle.
Good morning. How are things in Baltimore?
Well, we're great right now. I'm upstairs from that operations center that you see there. So I'm one floor up from the operations engineers right now. Right.
Well, let's start about the people that are joining us. Perhaps some of the people that didn't see the actual live broadcast of the launch that we did. Let's talk about what's happened in the 8 days since the launch. So what's happened and what's going on right now?
Yeah, so we had an absolutely beautiful launch on Christmas morning. I think it was the best Christmas gift under the tree for a lot of people, including our operations team and all the folks that have been working on this for so many years. Right off the bat, we got a beautiful launch from Ariane, put us right where we wanted to be as far as our velocity. That evening, on Christmas evening, we actually did our first mid-course correction burn, and that was executed flawlessly. We actually used almost the minimal amount of fuel that we needed to do that. So, and that burn didn't happen by accident. That was years in planning. So just, big shout out to our flight dynamics team and our Delta V team and our propulsion and all of our teams. So they pulled that off flawlessly at exactly 12 and a half hours after launch. Then the next day we did some more turn on of activities. We got our antenna deployed. Eventually we got into getting our another burn a couple days later. We did a small mid-course correction. And then the next day, we actually started doing our deployment. So we deployed our forward and aft UPS shells. We deployed that big tower that gets the telescope up away from the spacecraft. And then the pace started really picking up, and I had to. It's been such a blur. I had to write down just to make sure I didn't forget it all. On about 5 days in, we actually did our roll-up covers, and those roll-up covers come in 3 stages. We release a bunch of pins that hold those covers to the shell. We released those. They rolled up in two out of the 3 stages, and we held them there. And then on New Year's Eve, we did what I would think was our most exciting deployment, and that's where we actually deployed our plus and minus booms, our J2 booms. And you can see some footage here of the real thing when we tested this on the ground for the last time. So everything you're seeing in that footage is what we're doing right now. But those plus and minus J2 booms came out on New Year's Eve. We had a great New Year's Eve here in the Mission Operations Center. And the big thing about those booms coming out is that's when we plunged our telescope in the darkness. For the first time, our telescope has no more sun on it, and it's been cooling as it should ever since. And then over the last couple of days, we took a little bit of a break over the weekend, as you've heard in the news there, which was much needed for our team because they were going like gangbusters for that week. And then yesterday morning, we started what we're doing right now, which is actually pulling in the corners and actually tensioning up the 5 layers of the SUNSHIELD. So it's been an absolutely, just a whirlwind and a fantastic week since we've launched.
That's incredible. And so many congratulations. And I know that one of the things that's been sort of popular on the internet is we have a website actually where you can track where Webb is now. Can you give us a little bit of update?
Great.
So where exactly is Webb now?
I haven't checked it today. The last time I saw it, it was
Right.
roughly about 500, maybe 600,000 miles from Earth. We're on our way to L2. One thing you'll notice on that website that I think we get a lot of questions on is that it looks like we're slowing down. And that's exactly right.
Yeah.
We should be slowing down. So we want to go out and sort of we want to be pretty much absolutely stopped when we get to that roughly million miles away. And that's when we'll sort of be in our orbit around L2. So our velocity with respect to the Earth is actually coming down. You also see some temperatures on that page that kind of gives a little bit of a feel. We have thousands of temperature monitors all around Webb. We try to pick some that give you a little bit of a flavor of what's happening on the hot side and what's happening on the cold side. And so far, everything is performing as it should from a temperature perspective. I think some other things you'll see on our website is where we are on our deployments. And you should be able to track that all on our website. So, huge shout out to our media team that does those websites and does everything you're doing today, because we're a fast moving thing and you guys are keeping up with us. So it's, kudos to you guys.
We were talking a bit about some of the challenges with this, the resurgence of COVID has created. What's going on at the Mock and with your team to make sure people are safe? Tell me a bit about how you're dealing with the challenges right now.
Yeah, so like the rest of our nation right now, we're dealing with the surge right when we're doing all this. So we've known this. We've been in our rehearsal stage for a couple years now, since the reality of COVID hit the entire world. So we've started planning for dealing with COVID, a couple years back, and so we were ready for it. We weren't quite anticipating a surge like we just got right on top of our first week of the mission, but we have protocols in place to keep everybody safe. We do testing. We try to keep our numbers down. We do what we can practically, and then we do have cases. And our team handles that, and we keep those folks isolated. One of the things that has been a challenge is people who've worked a long time on this, and we had to isolate them. Now, fortunately, in this day and age, we can get them hooked up to our operations loop, and they can help us remotely from wherever they are. So we are handling it very well, but it's just another challenge that we just roll with it.
Well, let's talk a bit about what's going on today, because as we mentioned, there's something quite significant happening. So take us through, what's going to happen in the next, say, hour or so, and really what that means, what the significance of that is.
Yeah, so yesterday, we put out all these 5 layers of the sun shield, and they're just kind of, they're not really tight. They're kind of, and then actually what we've been doing since yesterday is our sun shield team, again, right downstairs right now. They're actually reeling in cables from each of the 6 pull points around the periphery of the sun shield. So each one of those corners actually has 3 cables related to it. One cable actually pulls it really, really tight, and then 2 cables on that corner actually are lightly pulled, and they're connected to the periphery all around the perimeter of the sun shield. And that's what gives us a very, very precise control over the shape of the edge. In addition to spreading the layers, we want to make sure that the layers are actually positioned correctly around the edge. So huge amount of engineering went into controlling those edges. So again, each layer has each corner has 3 cables, and again we have 6 corners, so you can start doing the math on those. And all over, we have 90 different cables that have been reeled in over the last day. As we tension layer 1, we're reeling in 90 cables. As we tension layer 2, we're down to 72 cables. And today we're really only working with 18 cables. So we've gone from 90 cables, and today we're working with 36 cables for layer 4 right now. When we start layer 5 in a little bit, we'll be down to 18 cables. And we have motors that actually reel all those cables in. Very precise, very, very well, slowly done. Those motors turn. And then eventually we'll turn all those motors off, and we'll be fully tensioned. When we get into layer 5 here in a little bit, you'll notice that we actually go around the corners. We tension each corner up separately. So that's what's going on today, and we'll finish up here shortly.
That's absolutely wonderful. So, just to kind of talk a bit about this heat shield, give us a sense about how large this heat shield is, and what are the temperature differentials? I mean, how cold is it on the cold side versus the warm side?
Yeah, so we always throw around the tennis court analogy. I guess if you play tennis, you know exactly what we're talking about. If you don't play tennis, you're probably like, well, I think that's big. I don't know. Roughly, I'm gonna use feet here. I know. It's roughly 70 feet. 70 feet long and about 54 feet wide. So you can see some dimensions there. Thank you for providing that in meters. So yeah, very, very large. It's one of the largest structures that has flown, that has been sort of robotically or automatically deployed. So yeah, quite large. Again, all the edge control, all the edge separation. And again, we're doing 5 of these. We're not just doing 1. So again, a huge shout out to our SUNSHIELD team. They've been at this for many, many years, and you cannot overstate what an engineering accomplishment this is.
The thing that's so exciting about so many aspects of the Webb. Oh, I see here we've got a graphic about the
Here's some
temperatures.
temperatures. Yeah, so yeah, this is dramatic. Again, we try to put this out on our website, but roughly we get about, again, in Fahrenheit, we get about 100-degree Fahrenheit drop per layer. Overall, we get about 600 degrees between the hot side and what I call our coldest temperature on the observatory, which is our instrument detectors. Our instrument detectors are running right around minus 400 degrees. So you could boil water probably on the front side of us, and then on the back side of us, you're almost down to absolute zero.
So the huge size of this has to do with just the general size of this observatory, in total, and of course this idea that it had to actually be folded up to actually launch inside the Ariane 5 rocket. And I just want to take you back a little bit through that launch. I know that this was something that was an incredible day for all of us. I'm sorry, I'm getting yes, absolutely. I'm just getting instructions that we have a wonderful chance to talk to another person that's had, been truly a historic day, Jim Flynn from Northrop Grumman. And so Jim, please introduce yourself to us and tell us a bit about how you're doing today.
Yeah, I'm Jim. I'm the original SUNSHIELD manager at Northrop Grumman, working in partnership with the NASA team. I've been involved in the SUNSHIELD all the way from the original concept development, through the design, all the build and test, and through this final great phase of deployments on orbit.
So let's talk a bit about the SUNSHIELD in details. I mean, for one thing, I mean, what an incredible story for you that you've been working on this for so long. Tell us a bit about what the SUNSHIELD is made of. I also, let's start with the technical. I'd also like to, ask you some personal questions about some of the challenges you faced, some of the things you had to overcome. But let's describe this SUNSHIELD. So to begin with, what is it made of?
So the layers are made out of Kapton E. It was made by DuPont, coated to get the correct optical properties for thermal performance. The bottom layer is 2 mil sticks. That's 0.002 inches thick, and the other 4 layers are 1 mil thick. Very, very thin material, but very, very strong when you're pulling on it. So it's very, very robust. In terms of the handling and the deployment, you have to be careful not to tear it or puncture it, but it's a very robust material. So basically, we make big, long rolls of this material, and then at our vendor that made the membranes for us at Nexolve in Huntsville, there's a very detailed process where we design, build, seam the gores together, and build the assembly that goes along with the big deployable structure system that you see here.
One of the things that I found really fascinating was how many of these actuators, these non-explosive actuators, have to work to get this thing to unfold. Could you describe a bit, what these actuators are and what has to happen?
So the majority of the actuators are really holding the folded SUNSHIELD down to the structure. We need to make sure that it's in a nice, repeatable fashion from all the ground testing, keeping it all, in a controlled fashion, and then releasing it very sequentially so that we have a very controlled deployment. These actuators basically hold that down and electrically actuate and release the system, in a very controlled fashion that we test on the ground and we've shown multiple times is successful.
One of the questions I had, of course, is that when you're testing on the ground, you have to deal with the effect of gravity during your test. And now where Webb is, up in space on its way to L2, it's different. I mean, how do you simulate that in your tests? The lack of gravity.
Yeah, so we had to kind of break the test program into pieces. At the big assembly level, you really just can't do that. So we made subsystem articles. We would hang them almost in a shower curtain fashion, deploy them out, offloaded like you would see in zero gravity. So it's really a building up of a lot of different test articles in different orientations to show how it would perform in a zero-G environment. So you have to do it kind of in pieces rather than all at once with the final build.
And what were some of the major engineering challenges? I mean, can you, over your many years working on the SUNSHIELD, what were some of the stories of, okay, at first we didn't know how to do this, and then we figured it out. What were some of the big things that stand out in your memory?
Yeah, I mean, originally we had an idea what this needed to look like, in its deployed state, but it was really, how do we take these 5 very thin membranes, fold them up and get them to fit within the payload fairing of the launch vehicle, and then be able to deploy it on orbit very reliably and, with a lot of confidence. So I think that's probably, in the big picture, just the ability to take these, 5 thin layers, fold them up, and then make sure that we know how we're going to deploy them to get to that final shape. That's probably the biggest challenge that we had, in the development of this subsystem.
I know that, whenever we've been talking about you, they've been saying, you've got to get Jim on this because he's the one that they feel was sort of the lead on this. I mean, the person that has been on it so long. How long have you been on this project? When did you start working on Webb?
It seems like my whole life now. I think probably maybe about 15, 16 years from beginning to end. So, so since the very beginning, since we were trying to figure out what the concepts were, building, maturing, and iterating along the way, and slowly improving the product and reducing the complexity, and then getting a very reliable system at the end.
Keith, is there anything you'd like to add to the story? I think you've been working with Jim for quite a while.
I mean, obviously, Jim is understating the challenges because he has overcome many along the way. So, the only thing I would say that people may not appreciate is the rocket launch itself and just getting the air out of all these layers. So, I'm sure Jim would like to add a little bit of detail there on how that was probably one of the biggest challenges.
Yeah, when you take the 5 layers and then you have to fold them and fold them again, you have to be careful about how that air is trapped in between the layers and how you can get it out in a controlled fashion. And that was definitely one of the biggest challenges, understanding what that environment was in the rocket, how quickly the air needs to evacuate the loads from basically this billowing inside the fairing. We ran a lot of tests. We built full-scale mock-ups in chambers that depressurized really quickly to verify the concepts. We had to design the system basically so that it was controlled through that depressurization environment and iterate several times in terms of making sure that that was a robust solution. So it was definitely one of the challenges, not just having it folded up and repeatedly getting it on orbit, but being able to vent that air that was trapped in between the layers in a controlled, reliable fashion so that the system basically could withstand those depressurization loads and deploy on orbit.
Yeah, what we're looking at here, the image that they have for us, was that spectacular, real image of the observatory pulling away from the rocket. And this was one of these things that I could hardly believe was real when it was happening. It was an absolutely gorgeous shot. And
DEU stop deploy.
oh, sorry, I'm just hearing an instruction from the mock. I was wondering if that was right. Yes.
Yeah, so they finished the layer 4 forward tensioning. They'll move on to the aft, and layer 4 is almost complete. Will be complete after the next major move.
Yeah.
Just amazing. One of the questions we've been getting from social media is that we had that image of the observatory pulling away.
At 622.017, ready to go to DEU operate frame 10. The command line looks good. You're go to execute. Execute.
Okay, so I guess I've heard that Jim needs to go to the console. That we're coming up on the very end of this. So Jim, thank you so much for joining us, and congratulations on everything, and best of luck for the rest of today.
Yeah, I just wanted to congratulate the entire team. It's just been a hugely talented team from beginning to end on the Northrop NASA side. A lot of brilliant people working a lot of hours and really a lot of dedication to get us here to this point. And there's a lot of people out there that really deserve a lot of credit.
Yeah,
and
I can confirm.
Kudos for the success that we're seeing here today.
Well, thank you so much for joining us.
All right, thank you.
At 622.019, we are ready to execute that. Clock looks good. You're good to execute.
Yeah.
So Keith, can you give us an idea? We're hearing these instructions coming over right now. What's happening at this very moment?
Yeah, so what you're hearing the voice of our Dep Ops lead, Nancy, and she's awesome, and she is coordinating between our flight operations team, which is actually sending commands up to the spacecraft, and she's sort of the liaison between that group of folks and actually our deployment engineers.
And OC, you are going to move the aft MTS motor pair.
And what she did there, she just told them to send a command to start running the motor on the aft tensioning mechanism. And if you look at the OBT right there, if you can see, you'll see 3 layers. And
OC, you can queue up the DEU stop. Roger.
You'll see the 4th layer rise here pretty soon.
And the motor status for the aft pair is moving.
And it's worth mentioning, you used an acronym, but this is actually a real-time animation that, although we can't see what's going on with the observatory, this is actually showing you what configuration it's in at the moment. It's based on the data.
And that brings up a good point. I know folks have been interested in, why don't we have cameras? Nobody would love to see Webb doing its thing right now than us. So it's, one of the things we really did want to put cameras on Webb. However, Webb changes shape a lot. You can tell over its deployment. It's going through multiple different configurations. So we just didn't need one camera. We would need multiple cameras in multiple locations. The other thing about Webb is it's very, very shiny on one side, and it's incredibly dark on the other side by design. And so we would have to take artificial lighting. Ultimately, we wanted cameras, but the engineering usefulness of those cameras just wasn't there unless it got really, really complex fast. The other thing is our cold side is really cold. So any camera on that side would have to be designed almost from the ground up to survive on that side. It would fall apart if not, and we'd have debris floating around. Possibly, it would, unless we started from scratch. So, and then the other thing, we're trying to keep our heat loads on that side very, very low. So all those things kind of combine together to say we really want these, but we just can't do it. So maybe from scratch, from day one, if we started over again, we could implement them in. So all that being said, we take all of our telemetry that's coming down from Webb. That's actually the numbers that we see on our screens and all the different information. Webb is incredibly instrumented. It's telling us everything about itself at all times, its position, where all these deployments are. But we take all that data and we synthesize it into a visual tool, which we're seeing on the screen right now. And we don't use it from an engineering perspective as far as this is what's really happening. The numbers tell us what's really happening. But our incredible OVT, our observatory visualization tool, they put a very good cool tool together, and this kind of gives us a little connection to Webb, even though we can't see it. This gives us that visual and spatial recognition of what's going on, and it's been very useful to our engineers as we work through different things that have been going on.
Wonderful. So, Keith, do you have any idea, are we sort of at a countdown about how much time it'll be until we know that this is completed?
Let's see, you should be doing layer 4 on the aft right now. That's quite a long motor move for this. So, and I always pull up here, I'm listening to a bunch of different operational loops. But they have got that started, so we should see that going right now. And again, right now on the app. Go ahead, Michelle.
Oh no, please go ahead, Keith.
No, I was just going to reiterate that we have 2 corners there. You can see in that view of the OVT, there's actually 2 corners. So we actually have 2 sets of mechanisms winding 2 sets of cables for each of those corners right now. You can see up in the corner there, maybe you can see in the corner, you'll see some of that data that's coming down from Webb that's counting up. Those are our instrumentation that tells us our position of our motors and how many, how our motors are turning and how fast.
I think that we have a few minutes here to maybe go back into some of the explanation as to why this heat shield is required. The whole idea about infrared astronomy and why it's so imperative to keep this particular observatory so cold. So maybe I'll just start by a bit of background about the infrared. And infrared astronomy is something that I've been involved in since I was right out of my PhD. I started working at the Jet Propulsion Laboratory in Caltech on the Spitzer mission a long time ago. Infrared radiation is something that we commonly think of as heat radiation. And infrared, the actual word infrared means beyond red. So this is a color that our eyes don't see. Our eyes are only sensitive to a small range of all of the colors of light, or as we say, electromagnetic radiation. And infrared is what we commonly think of as heat radiation. And so that's something that we need to keep the observatory very, very cold in order to detect heat radiation from objects very, very far away in space. And in fact, the science goals of Webb include detecting perhaps the farthest things we've ever discovered. One of the real advantages to infrared, as you see here, this is a Hubble Space Telescope visible light image of the famous Pillars of Creation. That's a giant gas cloud that's producing several stars inside it. Stars are being born. And when you go to the infrared, Hubble did have an instrument, NICMOS, that did see a little bit into the infrared. And you can see just what you're missing when you look just at visible light.
Console for a bit.
So those 2 images are both absolutely real. It's just that the second one is an infrared light, which is invisible radiation to your eyes. Infrared light has the ability to cut through dust. And this is one of the amazing properties. Just like you saw, if you want to see stars and planets forming, they do so inside giant clouds of dust and gas. And normally the visible light is completely obscured by all of that dust. There are other things like the very center of our galaxy. the Milky Way galaxy, which is a family of about 500 billion stars that we belong to. The center of the galaxy is on the order of about 30,000 light years away from us, a light year being about 6 trillion miles, the distance light travels in a year. And that is also obscured by big clouds of dust. We can't see into the center of our galaxy, invisible light. So there are so many objects that infrared is going to be really, really excellent to see. We may also have some roll-ins. Oh, here we go. Yes. Here's a really lovely roll-in showing you that Webb and Hubble, Hubble Space Telescope was designed mainly to see visible light, the kind of light that our eye sees. It did see a little bit into the ultraviolet and infrared. Webb is optimized and designed to see infrared. And amazingly, that allows you to see farther away in the universe. And that means farther back in time. The farther away you look in space, the longer light has taken to travel to you. And there's an amazing property of our universe. So the universe is expanding. Space itself is expanding. And as that light from the very early universe travels through space, the wavelength is actually stretched by the expansion of space. So light that might have begun from starlight and the ultraviolet or visible light from the first generation of stars, that wavelength of light has actually been stretched out into the infrared. And so if you want to see galaxies that are very far away and very distant, and here we actually see a graphic of how that works. A galaxy it seems to be receding from us in the expansion of space, and that light that would have started as visible or ultraviolet becomes infrared. So one of the amazing science goals of Webb is to be able to look back to a time probably only about 200 million years after the Big Bang. And this is the era that we think the very first stars and galaxies were forming. And so the amazing thing is the infrared light will allow us to actually see that far back, looking at the origins of galaxies and stars themselves. All right.
And Michelle,
So,
you
Keith,
can. Oh, I'm sorry. I'm just saying you can start to see, if you see, you can start to see that layer starting to rise up, layer 4 on that aft side. So slowly moving up now.
this must be very exciting for you. Can you give us a sense about your
A little bit like
emotions
grass
right now?
growing. But we like the grass to grow really, really slow. So
Yeah.
yes, this is exciting. I mean, yesterday we did not think we were going to get through the first 3 layers, but the team, again, the entire team just executed everything flawlessly. We were only planning to do 1 yesterday, but that went so well. They said, "Hey, can we just keep going?" And we almost had to hold them back a little bit. It was the day was getting long, and we want to make sure they're well rested. But they were eager to go, and so they're all excited this morning getting these last 2 out.
This was one of the things that we were talking about the live broadcast. We've just been following exactly when this is happening. Of course, the communications team does not dictate how the observatory is unfolded. The engineers do it when the conditions are right. And people around the world have been joining us. I actually was talking to somebody who is a fisherman up in Alaska, and I was telling him that, okay, now things are going faster than we expected now. And the thing that he said to me was, you have to respect the catch. Where the things go slow, and when the fish are biting, you keep going. And that's the amazing thing, that things were going so well that they decided to just go ahead and keep unfolding the SUNSHIELD. So that's what we're looking at right now.
And Michelle, I think you're seeing 2 different rooms on the broadcast. We have 2 main rooms. We actually have multiple rooms, but our one room that's shown below there, that's actually our flight control room. So that's sort of the nerve center of the entire mission ops center, and that's where actually commands get sent to Webb. So you can imagine that's a key room. We have our controller sitting on the front row. We have our mission ops manager, who's sort of the ringleader controlling the whole show. He's in there right now, along with our management team.